Happy day and welcome everyone. Today what we're going to be talking about are batteries and specifically electrochemical cells. So the first thing is we have two major types of cells. We either have this galvanic cell that we can see over here on the left, and we've got this electrolytic cell which is on the right. A couple of major differences. One is that this galvanic cell doesn't have any outside battery source, whereas the electrolytic cell does. We usually will be focusing on the galvanic cell in AP Chem, although we will have some problems that are going to be called, I call them the metal plating problems, and those would specifically be with an electrolytic cell. Okay. So one of the things that I'm noticing here is that this side, we've got two plates, an anode and a cathode. And our anode, similar to an anion being negative and a cathode, a cation being positive, we can see that the charges are correct there. Although in an electrolytic cell, it's reversed. The anode is positive and the cathode is negative. And one of the major reasons why is the electrolytic cell is a non-spontaneous reaction that we are getting to go in that particular direction. So we want it to go in the opposite direction from what nature wants it to do. So we can see that there's a battery that is provided there, okay? So that's really all we need to know about the electrolytic cell. So now let's just focus on the galvanic cell. So we can see that our anode is negative, our cathode is positive, spontaneous reaction occurs. It doesn't require an external voltage source. It's just going to naturally go and naturally move. And when that happens, we know that there are three things that we want to make sure we have related to each other. One is that if that's the case and it's a spontaneous reaction, or what we call thermodynamically favored, okay, so if it's thermodynamically favored, three things. One, our delta G is going to be what sign? If you said negative, you are right. Remember, we say Sarah eats, positive, positive, gross ham, negative, negative. So we want delta G to be a negative sign. Okay. The next thing is our E cell. And our E cell, we actually want to be a positive value. So again, we said Sarah eats, positive, positive. So we want Sarah eating to be positive. And the last thing is K. K is our equilibrium constant. And we know that K is equal to the concentration of the products over the concentration of the reactants. And if that's the case, and we want to favor the products so that we're actually moving our reaction in the direction as it's written without the addition of outside energy, which is how spontaneity is defined, then we want K greater than 1. So in order to be thermodynamically favored, these three things need to go hand in hand. Don't forget our delta S, which is entropy, the amount of disorder that it has, and our delta H, our enthalpy change. Those two do not tell us whether a reaction is spontaneous or not. We need to check to see, using the Hatz equation, for example, if it is looking at both of those. Okay. So let's take a look at these electrochemical cells here. And one of the cool things is that it's like a battery in your calculator in your car. They call it either the EMF, the electromotive force, or they'll call it the cell's potential. And these are given units of volts, they'll use voltage. These are the terms that are used to describe the potential difference between the electrodes in a cell. What causes the electrons to flow from an anode to a cathode? And let's actually write that down, and this is pretty cool. So if it is a spontaneous or thermodynamically favored reaction, then what I like to do is I like to say there's an ox on one side of the road, and there's a red cat on the other side of the road. Which way are you going to run? Toward an ox or toward a red cat? If you said red cat, that was a smarter thing to do. Okay, so we've got an ox and red cats. And there are a couple of things, and so we want to make sure that we actually go this way. And what's moving? The electrons are going to be moving. And so that's going to be our source of flow for the electron so that we can actually produce some electricity, right? So the AN stands for anode, the ox stands for oxidation, the red stands for reduction, and the cat stands for cathode. But there's also one more thing that's going to go along with this. The AN ox tends to be a black ox. And this red cat, we already said, is red. And if you ever use the wires or seen that we've got wires that we can connect with our electrodes, one side is usually red and one is black. So we want the red connected to the red cat, and we want the an ox connected to on the black side. All right. So it says, what causes these electrons to flow from the anode to the cathode? Similar to other spontaneous chemical reactions, it's all based on energy. It's all dependent on our energy and our energy changes. So there are two major types of cells. We already talked about this. There's the voltaic and the electrolytic. In a voltaic cell, the reaction occurs spontaneously without the addition of, if you said outside energy, that's correct. So while in an electrolytic cell, you need an outside source like a battery, the other major difference is in an electrolytic cell, like electrolysis, the cathode is negative and the anode is positive. So the electrons actually are going to flow opposite. So our electrons are going to flow opposite. So let's just kind of mark this. The cathode is negative and the anode is positive, which is actually the reverse. Okay, so this is for an electrolytic cell. And so then we're actually going, in this case, from the cathode toward the anode. And we're going to focus on voltaic cells. So remember, in a voltaic cell, it actually is the other way, which we said is going to be from anox, if we're doing a voltaic cell, anox towards the red cat. And your cathode will be positive here, and your anode will be negative. All right, so we're going to go from negative to positive in that case. Okay, so we've got these voltaic or galvanic cells. So a voltaic or galvanic cell is a device that forces what transfer? What's moving? Well, we know that the electrons are going to be moving. And they are going to move through an external pathway rather than directly between the reactants. Each half cell in a voltaic cell will have a different potential energy. So we're going to take a look at those. When the electrodes are connected by a circuit, the electrons are going to flow. The potential difference between the electrons is going to be measured in volts. And all a volt is it's a joule per coulomb. And so, because we know that a volt is not exactly a unit, but neither is the joule. So we'll talk about that later on. So this is called the electromotive force, which we can write as EMF, or we can write it as E cell, or we can just simply write it as the cell potential. Under standard conditions at 25 degrees Celsius, 1 atmosphere, and 1 molar concentrations, the EMF is called the standard EMF or the standard E cell. So you can see with this notation, they have that little 0 right there, and that just means that we're under standard conditions. So again, what we're talking about is 25 degrees Celsius, which, don't forget, if we switch that to Kelvin, usually we're going to want to be in Kelvin, is going to be 298 Kelvin. We can use 1 atmosphere. Typically, they will use atmospheres instead of kilopascals or millimeters of mercury. And we do want 1 molar concentrations. And this is really important because when we end up going to calculate K values, and if it's standard, we're going to assume that all of our solutions are actually 1 molar concentration solutions. Okay, so the cool thing is that when you want to know what your cell's potential is, all you have to do is figure out what is the EMF at your oxidation site, what's your EMF at your reduction site, and add them together. It's pretty cool. Okay, so half cell reactions are assigned EMF values in a chart, and it's called the standard electrode potentials in water at 25 degrees Celsius chart. It's important to note that these are all reduction potentials. I'm going to show you in just a second here. The oxidation potential is simply going to be, well, if reduction is written one way and oxidation would be the opposite way, where instead of, remember what we had said in the prior video, we said Leo says GR. And so if it's GR, then that means that we are gaining electrons for reduction. Well, then what would oxidation be? Oxidation is going to be our Leo. Leo says GR. So Leo means that we are going to be losing electrons. Losing electrons should be on the product side. Anything that's being lost is on the product side. So if we flip our reaction, all we're going to do is we're just simply going to reverse the sign. And an important thing to remember is potential actually doesn't change when we change the moles. So let's take a look at a chart and then we'll see how this ends up working. All right. So here is our chart, and there we go with our anox red cat. Go ahead and write this down. And our electrons are going to move, remember, from anox, black anox, and we can write in that this is black as well. And it's going to go toward our red cat. And again, the wire on here will be red on our cathode side. Again, the anode should be negative in sign and the cathode should be positive in sign. Okay, so if you notice here, a couple of things that we want to make note of. One is that as we take a look at how this is organized, we see that these are all reductions. If you take a look at where the electrons are with respect to the arrow, we can see that the electrons are all going to be on the left, which is why these are called reduction potentials. I also want you to notice, how is it arranged? Is it alphabetical? No, it doesn't look like it's alphabetical. It looks like it's arranged according to the potential, okay? So if we're higher up on the chart, this here should be the best at being reduced. So this is the best for reduction. Whereas if we go to the bottom of the chart should be the best for what? Did you say oxidation? Hopefully you said oxidation. So what we're going to do is when you take any two of these and you put them inside of a battery, spontaneously, what's going to happen is the one that's better for reduction, that's higher up, we're going to leave in this direction. The one that's lower in the chart, we're actually going to reverse it and we're going to make that our oxidation. And that is what should take place in our battery for it to be a thermodynamically favored cell. All right. All right, so let's take a look down here, and they wanted us to find zinc. So let's take a look again. It's not alphabetized, so I kind of have to just kind of scroll down. Oh, I see it right there, and I can see the zinc plus 2 electrons, and that's giving me a negative 0.76 value. Now, the way that this is organized too, we can see that there are, like, for example, there are 2 chromiums. There's chromium here, there's another chromium here, but this one's only gaining 1 electron. This one's gaining 3 electrons. So depending on how many electrons are being gained, that could be a difference. Also, if it's a solid anode, then going to a solid anode, then this is probably the one that you're going to want. You're going to want this one because this one is actually just turning the chromium into an ion, another ion. So just keeping that in mind on which one you would end up using. All right, so let's go back and let's put in this negative 0.76 for our zinc here. Okay, so we've got a negative 0.76, and the units are volts. Okay, so what is happening here? Well, this is reduction. We know that this is reduction because as written, it's gaining electrons, GR. So what if we had an oxidation? Well, if we have an oxidation, remember what we said, all you're going to do is simply change the sign. So instead of being negative, it's going to be a positive 0.76 volts. Now, this is important. If you heard what I said very briefly, an important thing to remember is the potential does not change when you change your moles. Change your moles all you want, it doesn't change it. Similar to like when we were doing in delta H values, for example, if you had, and we were doing Hess's law, if you multiply by 2, you have to multiply your delta H by 2. We're not doing that here. So in this case, the voltage is going to remain the same. So 2 zinc solid plus 2 zinc 2 plus 4 electrons, doesn't matter that we just multiplied everything by 2, it is still 0.76 volts. So keep that the same. So important to remember, the more positive the E cell value, the blank the tendency for the reaction to proceed in that direction, the more likely it is. So the greater the tendency. Why? Well, because we want our E cell to be positive. So as long as our E cell is positive, then it's going to go in that direction. Okay. Based on periodic trends, which group do you think would most easily be reduced and why? So think about it for a second. So we know that reduction means GR, gaining electrons. So the question is, which of the families on the periodic table want to gain the electrons the most? Did you say the halogens? If you did, that's awesome because we know that the halogens are so close to having just that one more electron so that they can have a stable outer electron configuration or a full, what we would say a full shell, for example. So we're going to say the halogens. They only require one more electron to have a full sublevel. Or sometimes it's an energy level. Okay, or you can say shell. Using your reduction chart, which of the following is the most easily oxidized? All right, let's take a look. We've got nickel 2 plus, aluminum 3 plus, or copper plus. All right, so let's find these on the chart. So I've kind of just marked them off here. I see my copper plus going to copper solid. So we don't want the 2 plus, we want the copper plus going to a copper solid. We have the nickel 2 plus here. And then we also have the aluminum going to a solid with a +3 charge. Well, if we take a look down here, we know that we said that the best for oxidation would be at the bottom of the chart since this is a reduction chart. So the best one should be aluminum, then nickel, and then the copper. Okay, so it looks like the aluminum 3 plus is the best for oxidation. Okay, so most easily oxidized. All right, so we already know this. We talked about when we're working with the galvanic or voltaic cell, it's also called the voltaic cell, oxidations at the anode, anox, reductions at the cathode, red cat. I always like to do this again. So this is our minus, this is our plus. Again, unless you're with an electrolytic cell, then it's backwards. So electrons flow from oxidation to reduction. They always flow from anox towards the red cat. And then the electrode that gains in mass is the one that starts as an ion and ends up as a solid. The electrode that loses mass, this is important. Okay, so when you look at what is going to be happening in a cell, let's take a look at a simulation right now. Okay, so in this simulator, I ended up putting zinc, a piece of zinc metal, which you're going to call that either your anode or your cathode. We're going to figure this out in just a second if I did this right. And I put that in a solution of zinc nitrate, so you always want to put it in its own solution. And then I took a piece of magnesium, also a magnesium solid, which again will be my anode or my cathode, the electrode, and I put that inside of a magnesium nitrate solution. Okay, so the red is on the left and the black is on the right, but I don't know if I did this right. And the way that I'm going to find out is I have to actually look at my potentials. So let's take a look at zinc and magnesium on my chart and see if I did this correctly. Okay, so I can see the zinc. That was the one that we already figured out right here. We've got my zinc right here. And then we actually put this in with magnesium, which is this negative 2.37 value right here. Okay, so based on these two values, this must be my reduction and this must be my oxidation. Why? Because the one that's higher should be better for being reduced naturally, okay? So what I'm going to do is I'm going to add my two numbers in order to get my E cell. So to get my E cell, I'm going to do a negative 0.76, and I'm going to add that, but this needs to be reversed. It needs to be flipped. And if I flip it, I'm going to get a positive 2.37. So let's go ahead and put this into my calculator, negative 0.76 plus a 2.37, and I am getting 1.61 as my answer. And that would be in volts. Let's take a look and let's see. That should be good because it's positive. So let's see if we did this correctly. So let's take a look at our simulator here and let's turn it on. Oh, 1.62. We're off by 0.01. Maybe there was just some error in either our chart or maybe theirs is a little bit different. Now, what I want you to see here is let's take a look at the molecular scale. And what I want to do is I want to take a look to see what is happening at each point. This here is called the salt bridge. And the salt bridge is going to show an exchange of ions. But what is more important right now is to see what's happening at the molecular scale here. And by the way, I did have my red done correctly and my black done correctly, which means this would be called my red cat. That would be my cathode. This should be called my black anox. So that's my black anode. And that's where oxidation would be happening. So let's take a look at what's going on. So remember, at the reduction site, we should be gaining electrons. And at my reduction and my oxidation site, I should be losing electrons. Notice here, when the electrons end up coming on, I actually plate more on. Let's take a look at what's happening when we're losing electrons at the oxidation site. So here I can see that this is going to be losing electrons, and the electrons are going to come up into the wire and go around actually. And when that happens, notice I'm losing mass. So it's kind of easy to remember because where you're gaining electrons, you're actually gaining mass. Where you're losing electrons, you're actually going to be losing mass because those are going to be turning into ions in solution. Okay? Hope that made a little bit of sense for you. Okay, so let's come back over here and it says, electrode that loses mass is one that starts as a blank and ends up as a blank. Well, if it loses mass, it should be starting off as a solid and ending up as an ion. And where does that happen? So we're going to put a little star over here. So we're going to say where it loses electrons is where it loses mass. That's how we're going to remember it. To remember it, we're going to say where it loses electrons, it loses mass. And what do we know? Where does it lose electrons? Leo, at the oxidation site. Okay, so the oxidation site is going to lose mass, and we know that the electrode that gains in mass is going to be the opposite of that. Okay, so it says label the Dr. UO anode and cathode, and then which one was actually going to gain mass. All right, so let's see if we can figure this out. I've got this going to a 0 charge. This is a 0 going to a +2. All right, so we've got that connected. The charge is going down. That must be my doctor, which means this must be my UO. So where's my anode, where's my cathode? Remember, it's an ox, and it's a red cat. So that means that here is my anode, and it should be a solid, by the way, so your anode should be a solid, which means if that's my anode, then this over here, cadmium, must be my cathode. So you do usually want to label the metal as your anode and your cathode. That's important. And then which electrode will gain in mass? Remember we said the one that gains in mass is the one that gains the electrons. So gains mass is going to gain electrons, which means GR. We're looking for the one that's our GR. That must be our cadmium. So the cadmium is going to be the one that will gain in mass. And again, typically they're going to be talking, when they say electrode, they're talking about the solid that's in the solution. Okay, we've got 2 half reactions in a voltaic cell. They're giving us this zinc, and then there's giving us this chlorate turning into chloride, kind of funny. Which reaction occurs at the anode? Now, once you figure out one, you can figure out the other one. Okay, so we only have to really figure out one of them. So the zinc is going from a 0 charge to a +2, which means our charge is going up. So that's going to be UO. And if it's UO, then we know that's our anox. And remember, just in case you need to do the connection, that would be your black wire. So that means that this must be my red cat. And again, that would be your red connection. All right, so our anode should be our zinc. And our cathode is probably more than likely going to be our chloride, our Cl-. Which electrode is consumed? This word consumed is the same thing as saying that is actually being used up or eaten away or losing mass. So when they say losing mass or consumed, we're looking for the one that loses electrons. And what do we say about that? Leo. So we're looking for our Leo. Write these things down so that you don't mess it up, right? So we're looking for our Leo, which means the oxidation site. That would be our zinc solid. Which electrode is positive? Well, positive is the cat, right? Like a cation is positive. So that would be our cathode is going to be positive. So which one's our red cat or our cathode? Should be the Cl-. And how many electrons are going to be transferred in this reaction? Well, we're going to use our LCM just like we did before, so the least common multiple between the two. And I can see here I've got 2 electrons, and here I've got 6 electrons, which means I would have to multiply the top one by 3, but don't forget, it does not change your potential. So if my potential is in this case a positive 0.76, it would stay that way. So now I'm actually just going to say that it's 6 electrons because I can just multiply that by 3, and that would give me my LCM. Okay, so metal plating we're actually going to do in a separate video, so that would be separate, and that would be talking about how electrolysis works. Usually they use an electrolytic cell for that. All right, and the last thing we're going to talk about today here is, again, just kind of a little bit of a recap of what we're talking about with the galvanic or the voltaic cell. So what you're going to have is you're going to have a metal inside of a solution on both sides of the cell. So this here is our metal. One of them is going to be our anode, one of them is going to be our cathode, and we're going to figure that out in just a second. The potential difference between the two sides is what causes your current to flow. So the electrons are going to move, and we'll figure out what direction in a second. One half of the cell will be the reduction, the other half is the oxidation. We already know that. There's a salt bridge that's in the middle. And I do want you to memorize this. What the salt bridge does, it's an electrolyte solution, and what it does is it maintains electrical neutrality. That's what I want you to remember. It maintains electrical neutrality by doing what? Well, because one side is going to be losing negative electrons, you want to replace those negatives. So it kicks back negatives onto that side. And the side that loses positive is going to kick back positive onto that side, and that's what keeps your battery going. Otherwise, your battery is going to stop a lot sooner, okay? So answer the following questions. It says which reaction occurs at the anode and the cathode and so on. So let's first take a look at our chart, and let's check to see if we've got nickel going to a nickel 2 plus and a potassium with a K plus. Let's check to see which one is our reduction and which one's our oxidation first. Okay, here we have it. I looked on our chart and it looks like our nickel is right here at a negative 0.25. Let's scroll down and let's see if we can find potassium. And there it is, down on this chart at a negative 2.92. Based on this, we know that the potassium is going to be the one that we need to flip and make an oxidation. We're going to keep the nickel as a reduction. All right, so let's go back over here and let's keep our nickel as our reduction. So this is going to be our reduction. Our red cat, which means that is the one we're going to hook our red wire up to. And the potassium is going to be our anox. And remember, it is the solid that is your what your anode is, and then or your cathode, depending on which one you're looking at. Okay, so we do know that. Let's actually take a look down here, and we're going to write some of this down where it says show your work below. Let's just do our work down here so that we have this straight. Okay. So I'm going to write our red cat equation here, and then we're going to write our anox equation there. Okay. So our red cat equation, we've got the nickel 2 plus 2 electrons yields the nickel solid, and that value was a negative 0.25 volts. Now the anox, we actually have to flip it. So we're going to reverse it right now, and we're going to make the potassium solid on the left instead. So we've got potassium solid, and then our arrow, and we had K plus an electron. And that value was a negative 2.92, but we're going to change it instead, and we're going to make it positive. So this is the one, since it's the oxidation one, this is the one that we have to reverse. Okay, so that's going to be the one that you have to reverse. All right, and so one of the things that they're going to end up asking us for is the overall reaction as well. So what does the overall reaction look like? Well, all we're going to do to get our overall voltage, our E cell, is we are simply, and it is a 0 because these are under standard conditions, so E0 cell. So if we add this up, we're going to actually get a positive 2.67 volts. And now what we want to do is we want to add everything up on this side. Now remember, your voltage doesn't change even if you have to multiply. So in this case, I'm seeing 2 electrons here and only 1 electron here. So what I'm going to do is I'm actually going to multiply everything by 2 on the bottom one. So I'm going to get a 2, and a 2. But remember, you do not multiply your voltage by 2. Okay. So now let's write down what our total would be. So I've got a nickel plus 2 or a nickel 2 plus aqueous. My 2 electrons are going to cancel out. Plus 2 potassium solids. And then our arrow. And now we get nickel solid plus 2 K plus. And again, that's going to be our E cell value. So now let's go back and let's answer these questions here. So which one occurred at the anode, anox? That's going to be our potassium. Where is our cathode? That would be our nickel. Which electrode is consumed in the reaction? Again, consumed means that it's losing mass. So which one is losing mass? The one that's losing electrons, which is our oxidation site. So that should be our potassium. Did you say potassium, hopefully? So losing mass, losing electrons, oxidation. Which electrode is positive? So remember, positive is our cathode. And we already said that our cathode was the nickel. And how many electrons are transferred? It's our LCM, and we already figured out that that would be 2 electrons. All right, so you use your reduction table. A spontaneous reaction should have an E cell that's positive. You're going to have to reverse one of the reactions. It's the one that's lower on your E cell chart or has a lower value, a lower voltage value. And then balance your electrons, and remember, it doesn't affect the voltage. I hope you enjoyed this video and you learned about how batteries and voltaic cells work. Happy day, everybody.